Dr. S.I.A. Philomen Raj, MSc, MPhil PhD, Retired Head Department of Physics, Madras Christian College, Tambaram, Chennai. He is presently serving as a guest lecturer in Loyola College, Nungambakkam, Chennai. He has a teaching experience of 35 years in Madras Christian College for UG and PG students. His field of research is nuclear physics, and he's presented about 30 papers in symposia organized by Baba Atomic Research Center, Mumbai. He has guided 50 MPhil students and about 100 MSc students in their projects. He has authored practical physics books for MSc and BSc courses. He's presently engaged in writing a book on nuclear physics for Printers Hall, India.
Welcome to UGC lecture series in physics for BSc Honours Physics. The title of the paper is Nuclear and Particle Physics of Semester 6, Paper 24. The first unit covers nuclear structure, basic properties of nuclei, mass, radius, angular momentum, spin, and we have been discussing about this. In our earlier lecture. And today we already started with binding energy, and today we will be bringing a derivation on binding energy. The contents of today's lecture will be binding energy and derivation of mass formula. So when you say binding energy, we need to recall what we said earlier. Any nucleus, it is containing maybe n number of nucleons, but when all of them are put together, the mass is not the same. There is a decrease in mass. So the decrease in mass appears as binding energy. So there is always a decrease in mass which appears as binding energy. Therefore, Weizakcer has taken this parameter and he has derived a formula for mass of a nucleus. Weizakcer mass formula assumes liquid drop model. When you say liquid drop model, it means the nucleus is behaving like a liquid, not like a solid or a gas. It is behaving like a liquid. And when will a system of nucleons can behave as a liquid? When there are large number of nucleons. Suppose I take alpha particle which has got only 2 proton, 2 neutron. If you put them together, they will not be forming a liquid. Suppose I take large size nuclei, then there will be more number of nucleons, and therefore they will behave like a liquid, like a single water drop. If you take single molecule H2O, that is not a liquid. If you take hundreds of H2O molecules together, then only it becomes a liquid. Therefore, what we have stated here is LDM is suitable only for heavy nuclei. Only for heavy nuclei, LDM is liquid drop model. And what Weizakcer has done is, assuming liquid drop model, he has derived the mass formula. So, in general, mass of a nucleus is always less than mass of the constituting nucleons. When you say constituting, that is the nucleons which make up the nucleus. A simple example, if you take helium-24, it has got 2 proton and 2 neutron. So, we know what is the mass of 2 proton, 2 neutron. Maybe it is 4 MeV. Let me say it is 4 MeV. Again, you may think why the mass is said in MeV. Already in the previous class, in the lecture, we have discussed that mass in the nuclear case, mass can be expressed in terms of energy because of Einstein's mass energy relation. So, mass need not be in kilogram, it can be expressed in MeV. Therefore, if you take, I will come back to the helium-24, it has got 2 proton, 2 neutron. So, maybe let me say it has got 4 MeV value of mass. But when all of the 2 proton and 2 neutron combined together, what you expect is 4 MeV. But it is 3.9 MeV. For example, I am saying 3.9 MeV, which means there is a decrease. When there is a decrease, it means decrease in mass, there is increase in binding energy. So, this principle was used by Weizakcer. So, the mass of nucleus is always less than mass of the constituting nucleons. The difference in mass is called delta M, mass defect. We have been discussing this earlier, but here I am just reviewing, I just recalling that, and we shall proceed. The mass defect appears as binding energy. If a nucleus doesn't have any mass defect, there is no binding energy at all. Now, Einstein's, so the Weizakcer formula is based on Einstein's finding that delta E equal to delta mc squared. Okay, this was said in 1905. Energy and mass relation, famous equation E equal to mc squared. Here we write delta E because change in energy, delta M change in mass. So we write as E, instead of E equal to mc squared, we write as delta E into delta M c squared. So the mass of the nucleus MaZ is less than, this is what is Z. Z is number of proton into mass of each proton. That's what we have written as MP, mass of proton, plus A minus Z. What will be A minus Z? It is number of neutron and mass of neutron. We take the mass of neutron. Therefore, a nucleus has got only proton and neutron. So we have taken, add up right side, we have got the number of proton and number of neutron and their masses. But the left hand side, you find that mass is less. As we said, it is due to the binding energy. Therefore, in the equation 1, what we have done is MaZ, A minus Z minus binding energy. So the minus binding energy is the reducing factor or reduction factor. Now, in this formula, all the masses are in MeV, as we already stated, because one atomic mass unit. What is one atomic mass unit? 1.67 into 10 power minus 27 kilogram. That is the actual kilogram mass. And equivalent, energy equivalent is 931. So based on that, we will be able to write this formula. So Weizakcer analyzed. So we said binding energy in the previous equation. We have said binding energy. In this equation, ZMP we know, A minus ZMN is known. Binding energy is not known. Therefore, Weizakcer thought of different contributions to binding energy from the basic principle or from what we reasonable assumptions he did. So we'll come to that. What are the parameters? So Weizakcer analyzed different parameters, namely volume, Coulomb, surface, Fermi, empirical. So in this equation, we have written volume effect. He considered volume effect. He considered Coulomb, the surface of the nucleus. And there is one term called Fermi term and empirical. We will come to that. And for you to remember, because it's a famous formula, to remember that we are just writing as VCSFE. At the bracket, we have just written VCSFE, volume, Coulomb, surface, Fermi, empirical. It has got 5 terms. So that 5 term, if you insert in equation 1, we will be getting the final mass formula. Now we'll go to the first one, volume term. For a heavy nucleus, binding energy per nucleon is a constant. See, we find binding energy per nucleon is a constant. Why is it for heavy nucleus? Just see this diagram. See, we have got this binding energy goes on increasing, and as A increases, it becomes almost constant. And in the y-axis, we have got binding energy per nucleon. So what we observe is, only when A is large, it is almost a horizontal line. Only when A is large, it is almost a horizontal line. This curve is an experimental curve. This is experimentally observed curve. They found out the binding energy of per nucleon for different nuclei, and they have observed this. So from this experimental curve, what we find is, in this region, B by A is constant. That's what I written. For heavy nucleus, B by A equal to constant. And when it is a constant, we say B is proportional to A. Binding energy is proportional to mass number. And in the next step, we write the proportionality constant as plus CVA. What is that CV? It is a constant. Constant appearing in the volume term. So proportionality constant is CV. And why it is plus? Plus because mass number increases, binding energy increases. Because B is proportional to A. Therefore, when A is large, binding energy will be large. Because more nucleons are there, each nucleon will contribute towards the attraction, and therefore binding energy will increase. We get this. Now, this is A. Why do you call as volume term? Why this is called as volume term? this binding energy is proportional to A, and A is already proportional to, we know that A is proportional to R cubed, because in the basic derivation for radius, we found that R is equal to R naught A power 1 by 3. R is equal to R naught A power 1 by 3, which means R is proportional to A power 1 by 3, or R cubed is proportional to A. And this R cubed is nothing but proportional to volume. For any spherical system, volume is 4 by 3 pi R cubed. So volume is proportional to R cubed is proportional to A. Now this binding energy is proportional to A. Therefore, it is proportional to volume. Therefore, we call it as a volume term. Now, as we said, just remember VCSFE. That's what we were 5 terms. Now, the first term we have done, and the equation we call it as equation 2. Now, we will go to the second term. Second term is Coulomb effect. Now, within the nucleus, there are a lot of protons. Each proton has got a positive charge. So, the presence of proton will cause repulsion. Therefore, the binding energy will tend to decrease. Therefore, before we make a derivation, we can easily say this particular term is going to be a negative term. This will only tend to decrease the binding energy, because the protons are repulsive and they will try to reduce the binding energy. So, that's what we have just written here. Presence of proton causes Coulomb repulsion. Therefore, the Coulomb energy of the nucleus, this part, say that equation I have written here, this we will derive. After this Weizakcer formula, we will derive this particular equation, like EC. What is that EC? It is the energy, Coulomb energy, and it is equal to 3 by 5. 3 by 5 is Z squared, E squared. Z is the atomic number, E is the charge of proton, 4 pi epsilon 0. Epsilon 0 is the permittivity, and R naught is radius constant, A power 1 by 3. This is not to be understood now, but we will immediately derive after this Weizakcer formula. We will derive, but here we will just assume. And here what we see here is, in this equation, 3 by 5 is a constant, 4 pi epsilon 0 is a constant, R naught is a constant, E squared is a constant. Therefore, all that constant put together, we call it a CC, Coulomb constant. The constant C, it is for the Coulomb term. So, we call it a CC. So, what are the variables here? Variables are Z squared, because Z will vary from one nucleus to another. So, Z is a variable and A is a variable. Only the Z and A are variable. All others are constant. Therefore, all other constants are put together. We will write a CC, Z squared, and this A power 1 by 3 is in the denominator. We take it to the numerator. We get A power minus 1 by 3. And why is this negative sign? Why is this minus sign? Because the presence of proton will reduce binding energy. So, the binding energy will reduce. Therefore, it's a negative contribution to binding nature. Now, what is this CC? As we already said, all the constants here are put together and we write as 3 by 5 E squared, all constants. We call it as CC. So, the negative sign indicates decrease in binding energy. Now, we have seen two terms, volume term and the Coulomb term. Now, after a break, we will continue with the third, 4, 5 terms. Welcome back to the physics lecture series. We have been discussing, just before the break, we have been discussing about the volume effect and Coulomb effect. Therefore, we have already discussed about volume and Coulomb. And for us to remember, we remembered like VCSFE, volume, Coulomb over. So, next is going to be surface term. So, we will go to the surface term. So, what is the surface term? Now, before we go to any derivation, we can just see a nucleus. If you take a nucleus, the nucleons, that is the nucleons, when you say nucleon, it is a common name for proton or neutron. So, the nucleon which are well inside the nucleus will have greater binding energy, and those nucleons on the surface will not have so much of binding energy. They will be loosely bound. They will not be attracted from all directions. They will be loosely bound. Therefore, before we make a derivation, we can easily say this term is going to be a negative contribution. So, nucleons will inside the nucleus will contribute more to the binding energy, whereas those nucleons which are on the surface will tend to reduce the binding energy. Therefore, this term is going to be a negative term. Now, we will go to the derivation part. See, generally surface energy is 4 pi r squared T. What is this T? T is coefficient of surface tension. Coefficient of surface tension of what? Of nuclear matter. Now, the Weizakcer formula is based on the assumption that a nucleus is behaving like a liquid drop. So, water has got surface tension, coefficient of surface tension. Kerosene or any castor oil has got highly viscous, and surface tension will also be high. So, we have got different liquids. Now, this nuclear is assumed to be a liquid. Therefore, it is assumed to have some surface tension. Now, the surface energy is 4 pi r squared T. Why it is 4 pi r squared T? By definition, maybe even in first year or even in school, we would have studied surface tension is nothing but what is the unit? It will be Newton per meter, force per unit length, or it can be energy per unit area. So, surface tension has got the unit energy per unit area. Now, this 4 pi r squared is the area. See, for a spherical nucleus, the surface area is 4 pi r squared. This is the area into surface tension, coefficient of surface tension. That will give you the energy, because this is area and this is energy per unit area. Therefore, we get the surface energy. Therefore, we can write this. Now, R is equal to, we know it is R naught a power 1 by 3, which we discussed in previous classes. R equal to R naught a power 1 by 3. Therefore, using that, we get 4 pi R naught squared T a power 2 by 3. So, that is because since R is equal to R naught a power 1 by 3, we get this relation. Now, this can be written as, this is surface energy. We are just writing as BS. What is that BS? It is binding energy due to surface nucleons. We wrote as BV, that is for binding energy for volume term. BC, binding energy for Coulomb term. Now, this is BS, which is binding energy due to surface nucleon, is equal to minus CS, that CS a power 2 by 3. What is that CS? It has got, see, in this equation, 4 is a constant, pi is a constant, R naught squared is a constant, T is constant. T is coefficient of surface tension of nuclear matter. So, that is a constant. Therefore, the variable is only a power 2 by 3. Therefore, we get CS a power 2 by 3. And why this negative? When you say surface energy, it is positive. But here, as far as binding energy is concerned, we are giving a negative sign. See, the Coulomb energy is positive, but binding energy is negative. Similarly, surface energy is positive, binding energy is negative, reverse of that. Therefore, we get minus here, minus. So, where CS is equal to 4 pi r squared T. This minus indicates a decrease in binding energy. The surface nucleons are loosely bound. Therefore, they will tend to decrease the binding energy. Therefore, that negative sign takes care of that. Now, what are the terms we are thinking? Like volume term, Coulomb term, surface term, Fermi empirical. So, we have finished 3 terms. Now, we will just go to the 4th term, which will be Fermi term. So, this Fermi term, it is of course, as the name says, it was included by Fermi. Initially, they had only the 3 terms, volume, Coulomb, surface. Weizakcer did that, and they calculated the mass. It was not in very good agreement with the experimental mass. There was slight deviation for certain nuclides. Then Fermi gave a term to refine the Weizakcer mass formula. So, it is called Fermi term. And what he included, it's an experimentally observed fact. Like if n is equal to Z, If a nucleus is having number of neutron is equal to number of proton, that is very stable. Example will be Y816, oxygen 816. It has got 8 proton, 8 neutron, and it's one of the stable elements, a stable isotope. If n is less than Z, that is number of neutron is slightly less than Z, or greater than Z or less than Z, both way. That is proton is more than neutron or neutron is more than proton. So here we have written n is greater than Z or n is less than Z. In both cases, stability slightly decreases. So it means if there is proton excess over neutron or neutron excess over proton, there is a decrease in binding energy. Therefore, this proton excess or neutron excess is a measure of instability of a nucleus. So if there is no proton excess or neutron excess, both are equal, it is very stable. For example, calcium 2040, it has got P equal to 20, number of neutron N equal to 20, it is very stable element. Similarly, tin also, tin or nickel. Now we continue with this Fermi term. So here, this for the Fermi term we write as BF, binding energy of the due to Fermi term. So it is proportional to, the binding energy BF is proportional to n minus Z whole squared. N minus Z whole squared. So why do you write this way? Suppose n equal to Z. Suppose here n equal to Z, this term vanishes. Suppose n is greater than Z or Z is greater than n, this term exists. And we are writing this as square, which means both will give positive value. N is greater than Z or Z is greater than n, this term is going to be positive because it is squared. When you square it, we don't get positive and negative. It will be both, in both cases it will be positive. N minus Z or Z minus Z whole squared. And why this A? That is, A is the ratio. Suppose I got proton excess, one proton excess, and A is very large number, then that effect will be small. Suppose I get one proton excess, for a nucleus with A is small, then the ratio is large. So the percentage of excess becomes large. So to take into account the ratio or percentage of excess, we take as A. N minus Z, how much is the excess over the total number of nucleons. And this part we write as minus CF n minus Z whole squared. So this proportionality constant is taken as CF. CF meant for constant appearing in the Fermi term CF. And here we give a negative sign. Again, as we said earlier, whenever proton is equal to, if proton number is equal to neutron number, this term vanishes. If there is proton excess or neutron excess, this gives a negative contribution. So the binding, what we observe experimentally or in nature, what we observe is nucleus with n equal to Z are stable. If n is not equal to Z, binding energy decreases. Therefore, that's what this equation reflects. If n equal to Z, this contribution is nil. Suppose n is greater than Z or Z is greater than n, this gives a negative contribution. Therefore, this take care of proton excess and neutron excess and negative sign. So this part BF equal to minus CF, I write n minus Z is written as A minus 2Z, because for any nucleus, what is important is A and Z. We refer only mass number A and the proton number, atomic number is Z. Neutron number, if you subtract, you are getting the neutron number. Therefore, what we know, this n is nothing but n is equal to A minus Z. So if you put n is equal to A minus Z, I am getting A minus Z minus Z, which is A minus 2Z. N is equal to A minus Z. If you substitute there, I will be getting A minus Z minus Z, 2Z. So we get this the equation. This is the Fermi term. So from this equation, what you get is, if n is equal to Z, BF equal to 0. That's what we are just telling. BF equal to 0. If n is not equal to Z, BF is equal to negative. So binding energy is maximum at n equal to Z. that is when n is equal to z, there is no, this term vanishes. Otherwise, this term becomes negative. So, why do you write divide by A, ratio of proton excess or neutron excess, the ratio of excess to total nucleon. That's what in the previous equation we were just discussing. This refers to excess, this is total. So, now we have just completed 4 terms: volume, Coulomb, surface and Fermi. Now, we will go to the last term, empirical term. So, that empirical term, as the term says, empirical, it's going to be only from experimental fitting. So, the last term we will be discussing later. Now, we have just written volume, Coulomb, surface and Fermi. So, next session we will just include the empirical term and we will be able to get the final mass formula. Let us summarize what we have been discussing today. Our aim is to derive the Weizakcer mass formula, and for us to remember, we had the mnemonic like volume VCSFE, and we have just completed the volume term, Coulomb term, surface, Fermi, and empirical term we will be discussing in the subsequent lecture class. But however, to check our understanding, we will just pose a few questions. Why is it that Weizakcer mass formula is more suitable for AV nuclei? Just think about it. Maybe next class we will discuss more. So, calculate the increase in binding energy for a decrease in mass of 1 AMU, 1.1 AMU. That also you know that 1 AMU is 931 MeV. Accordingly, just calculate. We'll check the answers next class. Then derive an expression of Coulomb energy of nucleus. So, already we written that EC is equal to 3 by 5. So, that part you just try deriving. Next class, I will also present the derivation of the same. And we were talking about the coefficient of surface tension of nuclear matter. So, estimate a value for coefficient of surface tension of nuclear matter, assuming the surface energy to be CS, to be 13 MeV and R not equal to so much. So, if you just look into the surface term, you will be able to get the answer. So, with these questions, we will just wind up for the today's session. We will be continuing in the next session. Thank you.